in the photoelectric effect, we saw that light that we typically consider to be a wave was exhibiting particle properties as well. And that leads us to this, it's known as the wave-particle duality. So it's basically the idea that we can't really tell whether light is either a wave or a particle. So it depends on the experiment that you're conducting and the measurements that you're making as to whether or not you'd say that light is a wave or a particle. And as a result, we'd say that light has both properties, and as I said, it's known as the wave-particle duality. Now, the interesting thing about this idea, the wave-particle duality, is that we typically was developed by looking at light first of all, but in 1924, a scientist by the name of de Broglie, he kind of looked at that result and said, well, hang on a second, if light being a wave has particle properties, perhaps then particles might actually exhibit wave properties. So this sort of flipping the idea around, instead of looking at waves having particle properties, might now see that particles might exhibit wave properties. And so skipping over a fair bit of the detail of what that actually means, we're just going to jump straight to looking at how we can sort of relate these two things together. If we look at photon energy, as we saw from Max Planck, energy of a photon is given by hf, and because we know the relationship between f and lambda, we can write that instead as hc on lambda. And if we then also look at Einstein's equation, the mass-energy equivalence, so basically linking those two properties of mass and energy, we have an expression for energy given by E equals mc squared. So we've got these two expressions for energy, and we can basically say for a photon they're the same thing. So we can then say that hc on lambda is equal to mc squared. Now you notice there that we've got c's on both sides, so we can cancel out the c's, so we end up with h on lambda is equal to mc. Now if you look at this property here, or this expression, m times c, that's mass times a speed, so that's actually the photon momentum. So momentum being very much a particle property, if we take that just one step further, we could write then that lambda is equal to h on p, so mc being equal to p, solve for lambda, we end up with lambda being equal to h on p. Now that value for lambda is known as the de Broglie wavelength. So basically what it means is if we know the momentum of a particle, so if we know this value of p, we can calculate what the value of the corresponding wavelength for that particle would be. Now typically if you look at the value of h, it's very, very small, so typically you're not really going to see the wavelength of anything that has a lot of momentum. So particles typically you can't observe their wave properties, but if the particle is small enough, then it is possible to observe those wave properties. And in fact in 1925, two scientists by the name of Davison and Germer were able to show, or were confirmed this idea of a de Broglie wavelength, and they did that by using electrons, and they observed a diffraction pattern of electrons after they were shot through a crystal target. So by observing the pattern of the electrons, so that if you think back to our previous waves unit, the diffraction pattern means that there's some regions where you get lots of electrons appearing and other regions where you get none. So, and then sort of that alternating bright and dark kind of idea. In this case, an alternating intensity of electrons that are hitting at each point. So by observing that diffraction pattern of electrons, they confirmed that there is in fact a wavelength that's associated with matter. If we then take this idea one step further, and again linking back to something we've done before, so subtopic 7.1, we looked at the energy levels in atoms, where electrons could only exist in stable orbits. Then we sort of briefly alluded to the fact that they're explained by the Bohr model. If we look at Bohr's model of the hydrogen atom, we can now explain exactly how those stable orbits exist. So with Bohr's model of the hydrogen atom, that proposed that stable electron orbits were a certain, they were related to the de Broglie wavelength of the electron. So those orbits had a circumference that was equal to, or that was a multiple of the de Broglie wavelength. So we can again look at a little bit of maths behind this, and identify then that if we look at a little bit of a diagram to begin with, so if this is say the nucleus, if we have the first orbit around here, that's going to have a certain radius, we'll call that R1, and that's going to be, so if we look at the total distance around or the circumference there, that would be lambda 1. If we then go to the second energy level, the radius there is R2, and we could then fit in 2 de Broglie wavelengths, sorry, that should be lambda E, not lambda 1, and then if we go to the third one, so on and so forth, what we'd see there is that we could fit in 3 de Broglie wavelengths of an electron, and that would correspond to the radius R3. Now, if we generalize this, you can see that the circumference of each orbit is given by 2 pi n, so n being 1, 2, or 3, and that's equal to a certain multiple, so n multiples of the de Broglie wavelength. So when n is equal to 1, 2 pi r is equal to lambda e. When n is equal to 2, 2 pi r2 is equal to 2 times lambda e, and so on and so forth. If we identify, though, we've got the de Broglie wavelength for an electron, we know that it's given by h on p, so we can substitute that in and instead write 2 pi rn is equal to nh on p, but given that we're dealing with electrons, we know that electrons have mass and they'll be moving with a speed around that orbit, so we can instead write that as nh on mv. Now, a little bit of a step here that I'll explain once we've gone through it. We're going to multiply mv up over this side with the r, and we'll then end up with nh on 2 pi. Now, that's an equation that's an important one to note. The reason for this one, this quantity on the left-hand side is the angular momentum of the electron. So as the electron is orbiting, it has a certain angular momentum, and that's measured by, or calculated by, its mass times its speed multiplied by the radius of the orbit. So another way of stating this is that the angular momentum of the electron is a whole number multiple of Planck's constant over 2 pi. So just a slightly different interpretation of that particular equation. The last thing we'll just note here, not something that we'll go into in lots of detail, and we've sort of already seen it back in subtopic 7.1 anyway. The energy associated with each energy level for hydrogen is given by a fairly simple equation, and I'm not going to go through any derivation for this at all. It's just simply that the E for the energy for the nth level is negative 13.6 over n squared, and that will be in electron volts. So again, that's an equation that's in the data booklet. If you think about it, when n is equal to 1, then E is equal to negative 13.6, so the ground state for hydrogen is negative 13.6 electron volts. So there's some information that sort of follows on from Planck's discovery, the photoelectric effect, and then leads through to this idea of matter wave, so matter having wave properties, so this wave-particle duality kind of idea.